Let's tackle question 8 of the 2018 Edexcel A-Level Further Mathematics, Paper 1. This question is 6 marks, which gives us about 7 minutes to solve. So, this question is a matrix proof by induction question. It's asking us to prove that a matrix of 5, minus 8, 2, and minus 3, all that to the power of n, equals 4n plus 1, negative 8n, 2n, and 1 minus 4n, as shown. So, this is a proof by induction question. So before we dive into this question, let's first revise what is proof by induction. So, proof by induction is a general way to prove that a statement is true for all positive values of n. With this, there are 4 steps. Step 1, we need to prove the base case. Prove that n equals 1 works, okay? Second, we need to assume that n equals k holds true. This is our assumption step. The third step is to prove that n equals k plus 1 will work by using the assumption that n equals k works. Okay? A bit confusing, but this is the inductive step. And once we've done that, the proof is complete. Now, what is the intuition behind this? Think dominoes. Okay? So, here's a standard dominoes falling. Now, if we take 2 dominoes, k and k plus 1, if we can prove that when k falls, that k plus 1 will also fall, then that should be the case for every domino. Any 2 dominoes, if the first guy falls, the second one will also fall. But in order for the domino chain to start, the first domino must be pushed over. This is the base case. Okay, now that we've got that, let's go through a basic example of proof by induction. So, this example is asking us to prove that for all positive values of x, is fx an even number? Now, I know we can just do this in a blink of an eye. We can just take out a 2, and that's proof. But let's prove it via induction first. Firstly, we need to say, okay, for it to be an even number, it must be divisible by 2. Okay, so step 1, we need to prove our base case. If we put x equals 1, is it even? f1 is 6, which is even. Okay. Next up, we need to assume that x equals k holds true. Okay, fk, let's say that's an even number too. Step 3, we need to prove that when x is k plus 1, that is also even, okay? So if we put fk plus 1, it becomes 2k plus 6. Now, if we look at the difference between the two functions, fk plus 1 and fk, we can simply minus them and we get 2, okay? Now, fk plus 1 is simply fk plus 2, plus the difference, right? Now, fk, this bit is divisible by 2 from step 2's assumption, and the remainder, again, is an even number, hence we can take out a 2. Now that we have proved it, the statement holds for all positive values of x. Now this symbol here, it is simply the set for all positive values. Now, if we go back to the question, it's matrices. So, we're going to have to know matrix multiplication. Let's go over that again. Okay, matrix multiplication is quite simple. We are essentially multiplying each row by its corresponding column. So as you can see, the top left position is row 1 into column 1. Top right is row 1 into column 2. Bottom, same thing, row 2 into column 1 and row 2 into column 2. Now, how do we multiply a row and a column? It's again simple. For example, if we look at this, we have our row AC, which is the first row of the first matrix, and we have the first column of the second matrix, EG. Now, if we were to multiply these together, we simply multiply A and E, C and G, and we add those two together, like so. Now, if we go back to the question, first we got to prove our base case. Thus, when n equals 1, is the proof satisfied? If we put them in, it's satisfied. Now, we're going to assume that n equals k holds true. This is our assumption step. Step number 3. We're going to now use this to prove that n equals k plus 1. Now, there's a trick we can do here. Since we're dealing with powers here, right? We're trying to prove n equals k plus 1 is true. Now, n equals k plus 1 is simply, if we use power laws, x to the power of k plus 1 is essentially x to the power of k into x. There we go, we can use this now. So we can rewrite the matrix to the power of k plus 1 as a matrix to the power of k into the matrix, as so. and simply we can multiply this out. Once we've done that, we can now rearrange it to the original matrix form, where n is now k plus 1. If we can rearrange that, we have proved it, as the relationship holds for k plus 1. And as so, we have proved it. Hence, the statement is true for all positive integers. This video was brought to you by Memseed Academy.